Welcome to Data Skeptic All About Surveys, our season about survey design, interpretation, and methodology. Let your voice be heard at survey.dataskeptic.com. If you look at a large enough populated area, a big city or larger, it can take a lot to run that city. It might even be one person's full-time job to estimate things like the rate of unemployment, because that's going to tie into some projection of budgetary needs for the increase in social services. That makes these very challenging predictions critically important because you're going to make an important decision based on them. So when someone like a labor economist wants to apply predictive modeling, they need good data and good models. One of the sources for data we're going to talk about in today's episode is actually the feature of last week's interview. The Panel Study of Income Dynamics, or PSID, is one of the inputs to CAREER. I hope you could hear me saying that in all caps. It's an acronym. CAREER is a transformer-based model that uses transfer learning to learn representations of job sequences. Think about your own career. While for many people it's filled with a couple of good twists and unpredicted turns, it's generally also filled with a lot of predictable things. You went from data scientist to senior data scientist to managing data scientist. That sounds quite natural. Junior data scientist to senior data scientist to senior graphic designer. That's a little weird, but possible. And in the same way we can apply our intuition to sequences like that. Well, anytime I rely on intuition, I know that's a good opportunity to use machine learning instead. So in today's interview, we get into how to use this survey data to make predictions about future career paths.
My name is Keyon Vafa, and I am a Ph.D. student in computer science at Columbia University. Broadly, I'm interested in developing machine learning methods for the social science. So my background is in machine learning, although I've done a little bit of work in natural language processing, NLP, and statistics. Most recently, I've been focusing on combining ideas from all these fields so they can be used to analyze surveys in the social sciences. So the space of social science surveys is so vast, so I've been focusing on one kind of survey data set, namely those that can be used to help answer questions that labor economists are interested in. Although I'm interested in developing machine learning methods more broadly that are applicable across a wide range of surveys in the social sciences.
A lot of industrial applications of machine learning, which can happen in any industry, including a social science one, but the ones, I guess, that make headlines tend to have the benefit of really big volumes of data to train on. I don't know that that's often the case in the social sciences. Could you highlight any challenges in applying ML there?
Yeah, I mean that's sort of the big challenge that we were focused on. That a lot of social science surveys, not every social science survey, but a lot of them are focused on very small data sets, or small by the standards of machine learning practitioners. And machine learning methods work best when they are applied to large data sets of, individuals or images or text. So I think the best place to start is to talk about survey data sets. So specifically, an important class of data sets for labor economists are longitudinal survey data sets. And these are data sets that follow individual workers over a period of time. So that the first year that an individual is in the data set, they'll be interviewed by a surveyor. And the surveyor will ask questions about their life and work. What's your occupation? What's your most recent educational degree? What's your wage? And so they'll answer all these questions either on the phone or in person. And then the surveyor will hang up the phone or go home until the next year when another surveyor will come and ask the same set of questions. What's your occupation now? What's your most recent educational degree now? What's your wage now? And this process will repeat itself every year until the data collection process is complete. And so by the time that the survey is over, we have for each individual in the data set a detailed history about their entire career trajectory. And so the size of these data sets vary, although they typically contain about thousands of individuals that are followed from year to year. And so what's the goal of these survey data sets? They are designed to follow a nationally representative sample of the broader population so that social scientists and other analysts can make inferences on these smaller data sets that then extend to the broader population that they care about. So one example is the gender wage gap. If a labor economist wants to estimate the gender wage gap and has access to government records of all 150 million or so workers in the US, they can estimate the true gender wage gap close to exactly. But in practice, This data can be very difficult to get. They're not going to give it to a machine learning PhD student like me so easily. So instead, the analysts will estimate the quantities they care about on these longitudinal survey data sets, and they'll consider the roughly 5,000 or so randomly sampled individuals in these data sets, and they should extend to the broader population. And so I want to stress that even though the examples I'm focusing on are related to labor economics, the survey data sets are used in a wide variety of fields like political science, public policy, public health, education, nutrition, and so on and so forth. The most common survey data sets are the National Longitudinal Survey of Youth, or NLSY, and the Panel Study of Income Dynamics, or PSID, which has been following individuals since the 60s and 70s.
Can you share a few details on the surveys that we've been discussing, where they're coming from and sort of how they're collected?
So we focused on two kinds of survey data sets, the Panel Study of Income Dynamics, or PSID, and two cohorts from the National Longitudinal Survey of Youth, or NLSY. So PSID is a longitudinal survey that began following a cohort of Americans since the late 60s, and it has added individuals throughout the years. It began as an annual survey, but it has become biannual since the late 90s. So NLSY is similar in a lot of ways, except it follows a cohort of workers who are all similarly aged. So one cohort of NLSY follows workers who were between 14 and 22 when the survey began in 1979. And then another follows a different cohort of individuals who were between 12 and 17 when the survey began in 1997. So this work that I'm talking about today, Career, is an interdisciplinary effort. It's work with me and my advisor, David Bly. We both come from computer science, along with Susan Athey at Stanford University, who does work in economics and also computer science, and her students, Emil Pellicott, Tian Yu Du, and Ayush Kanodia.
And are there any challenges in scaling up that representative sample? Do people find that it truly does describe the whole population?
So there are a lot of challenges, and over the course of some of these surveys, they do have to adjust the individuals that they're in. If, say, some demographics are overrepresented and some are underrepresented, they'll need to make some adjustments, not only in terms of who they actually follow in the survey, but also most of these surveys include weights that are the surveyor's sort of best estimate of how we should adjust the estimates that we're making on these data sets to account for the fact that it's really, really difficult to get a true nationally representative random sample.
Well, I see a lot of value in these surveys, but I also know that there's never a problem having multiple lines of independent evidence, all hopefully telling the same story. Now that the world is so much more digitized than it has been in the past, are there other ways we could start to measure the same thing?
Yeah. So that's exactly the sort of thing, the goal that we set out to solve. We were so interested in how can we use these surveys to make meaningful estimates and to estimate things that we care about, but also take advantage of other data that has been collected either digitally or non-digitally. And so the specific perspective that we focused on is that many of the analyses that are fit to the small survey data sets involve fitting predictive models to the survey data. So these are models that take in as input something about a survey, and then the goal is to make a prediction about some survey quantity. So for example, one method for estimating gender or racial differences in unemployment is to fit models that predict whether an individual will be unemployed as a function of other covariates, such as an individual's education, for example. And so these predictive models are not just limited to predicting an individual's next job. One method for estimating gender or racial wage gaps is to build models that predict wage and then compare across gender or race. But let's focus on predicting an individual's next job, since this is sort of the primary thing that I've been focusing on for now. And so, as we mentioned, these data sets are small. So it's been in the past, it's common to fit linear models from the features that we care about, such as demographics, current job, to predict an individual's next job. So they're linear, and they also don't typically include an individual's full job history to make these predictions. And this is because an individual's full job history is very, quote unquote, high dimensional. There are many possible career trajectories that an individual can take. And it's just infeasible with the small survey data sets to include an indicator for every possible history that an individual has. So to predict an individual's next job, the only parts of history that they typically condition on are an individual's current job and years of experience that the individual currently has. So our goal was to develop ML methods that use an individual's entire work history to predict their next job. Because the major challenge is that survey data sets are small, many machine learning methods that are trained from scratch require large data sets and corpora to make good predictions. So instead, we use an idea from machine learning called transfer learning, which pretty much means using large scale auxiliary data to make predictions about the smaller data sets we care about. So specifically, a kind of data set that is becoming more common nowadays is large scale data sets that contain resumes or worker profiles of individuals that have been scraped online. And we were given access to one of these data sets by Zippia, a career planning company, and it contained the resumes of about 25 million American workers. Like the survey data sets, each resume could be transformed into a sequence of jobs, but it's difficult to use these resume data sets directly for economic analyses. They're missing information such as wage. There are concerns about data quality. They may not be randomly sampled or representative of the population. So we were interested in trying to use this large volume, albeit imperfect, to incorporate that into our predictions of the small scale thing that we care about, and that is the survey data sets.
When you say you were given 25 million resumes, that's a great data set, but I'm guessing that's a few zip files of PDFs. Is that correct?
Yeah, so the data that we had access to had been nicely cleaned for us. It was in a kind of JSON format, which means that someone else had done the kind of difficult pre-processing. Some of these resumes could be PDFs, some of them could be worker profiles that were online. So we got access to the data in a unified format that for each worker included a JSON file, which is sort of one way to think about it is that it's kind of like a table of each job that a worker had over their career, maybe the descriptions of those jobs, unified codes that economists and other social scientists use to transform individual specific jobs into categories that contain anywhere from 300 to 1,000 categories, depending on the job categorization scheme.
Can you share a little bit more about those codes? My personal experience, I've taken some surveys where I have to fill it out, and the taxonomy always seems a little unusual to me. I never find the label that I feel really describes me. Do you have any thoughts on the available labels?
Yeah, this was something that was pretty new to me. So I came into this from a machine learning background, and this is sort of the first time that the data is always important, but this is sort of the most important that the data has been. So this is sort of dealing with all these different data files and crosswalks was kind of new to me, and so I found that it seems like every kind of data that we have about jobs uses a different categorization scheme. There's some from
Yeah.
OCC, there's OCC, there's ONET, there's all these different kinds of things. The kinds of data that we cared about, the resume data set that we want to use for the survey data set, these all have different categorization schemes as well. So we use the unified categorization scheme. The scheme is called OCC 1990DD by Dorn and Autor. And we sort of use that as a unified thing, and that contains about roughly 330 different job categories.
Like so many of you out there, I love Notion, our sponsor today, and I use it every day for notes, docs, and project management. It's a great tool, and I'm going to assume most of you have already tried it, because today I want to tell you about the new buzz around AI, specifically what Notion has just launched in their new incredible tool, Notion AI. Notion AI helps you work faster, write better, and think bigger, doing tasks that normally take you hours in just seconds. Everyone's aware of the recent advances in large language models, and Notion has one of the most impressive rollouts of it. They have some really cool other tools like helping you rewrite a paragraph to sound more professional or more casual or one of the labels you choose. Just tell Notion AI what to do, the more details the better. Have it write a blog post, make an outline, brainstorm ideas, or summarize a whole bunch of documents. Notion AI is an impressive choice for writing, summarizing pages, finding action items, inline translation, and whatever you need to have the IDE for running your life. You can select any text in Notion and click Ask AI. For a limited time only, try Notion AI for free when you go to notion.com/dataskeptic. That's all lowercase letters. Notion.com/dataskeptic to try out the incredible power of Notion AI today. And when you use our link, you're supporting the show. This is a limited time offer. Try Notion AI for free right now at notion.com/dataskeptic. Learn, collaborate, and connect with the global data community at the 2023 Data Connect Conference on July 20th and 21st, hosted by Women in Analytics. The annual Data Connect Conference brings together 1,500 industry leaders, technical experts, and entrepreneurs to discuss the latest in data, analytics, machine learning, and artificial intelligence. You'll hear from 50-plus thought leaders like Cassie Kurakov, Chip Wynn, Stephanie Domas, and Wendy Batchelder, Data Connect's multiple tracks cover a range of topics, allowing each attendee to create the optimal agenda tailored to their interests and experience. You'll also find non-stop networking opportunities to collaborate with peers and connect with experts. Ready to learn something new? Enhance your conference experience with expert-led workshops where you'll learn in-demand skills from seasoned professionals. Or book an Ask an Expert session to meet with a specialist one-on-one during the conference. Data Skeptic listeners can get 15% off regular or virtual conference passes using the promo code DATASKEPTIC. So clear your calendar on July 20th and 21st, 2023. If you're in or can get to Columbus, Ohio, go on site. If not, get that virtual pass. Either way, you can get 15% off with promo code DATASKEPTIC. Visit www.dataconnectconf.com. That's dataconnectconf.com.
So then when you take that JSON record and convert it into an occupational trajectory, is that sort of an array of these identifiers?
Yeah, exactly. So you can think of each job trajectory as a sequence of categories. And so the specific way that we encoded these categories was numbers. If there are 500 different categories, each job is just going to be a number between 1 and 500. So for example, one sequence could look like, 285, 285, 390, and maybe that's someone who spent 2 years as a bartender before becoming a waiter or waitress. And this is similar to ideas from natural language processing or NLP. Because in NLP, a lot of times you're working with sequences, not of discrete jobs, but of discrete words. And so the ideas that we took for taking sequences of jobs to predicting the next ones were very inspired by ideas from NLP. So maybe a good analogy is ChatGPT. So ChatGPT, it's an amazing chatbot, but it's not just trained on transcripts of chatbots of people using the chatbot. There just aren't enough people using the chatbot for it to learn all about, humanity and the English language just from people using chatbots. So instead, it first uses a large portion of the internet as auxiliary data, where it learns about common types of sentences and syntax along with world information. But then to make it tailored to be a good chatbot, it's then adjusted on a relatively smaller number of real conversations with people, so it can harness all this information and use it in chit chat in chat form. So this is analogous to what we do, although on a much smaller scale. Instead of initially training on a large portion of the internet, we initially train on a large data set of resumes. And instead of adjusting the model to be a chatbot, we then adjust the model to harness this information to make predictions of future jobs on survey data sets that are collected for the social sciences. And by the way, the approach that we use is it's called career. It's a backronym. I won't get into how we had to force it to stand for something, but yeah.
And do you have any general observations about the exploratory data analysis phase? I know sometimes people will switch careers, so there must be a lot of stochasticity to it, but at least my own career is fairly linear and predictable. What is the average person like?
So this sort of would also fall into the category of things I learned about from doing this project and collaborating with these economists, that where the data comes from, what the data looks like data quality is so important. And so I made the analogy before to NLP, but one way that sequences of jobs are going to be different than sequences of words is that sequences of jobs are going to repeat far more often than sequences of words. It's rare to have two words repeat or three words, whereas it's very, very common for someone to work in the same job 2, 3, 4, 5 years in a row. And by the way, we use years as sort of our time step as how we divide
Mm-hmm.
the sequences. And so one change we made to account for the fact that jobs tend to repeat far more frequently than words do is, although we adapted models from NLP, we changed them to incorporate the structure that we knew that jobs would tend to repeat more often than words do. So we added into our component that the model makes predictions in two stages. In the first stage, it tries to predict whether an individual will switch jobs or not. And then if the individual doesn't, if it's predicted to not switch jobs, then the prediction is very easy. There's a 100% chance that the individual will be in the same job as they were in the year before. And then if it does predict to switch jobs, then it's a little bit more difficult. And then we sort of lean back into the traditional way that next jobs or next words are predicted in natural language processing.
Well, I'd love to dig into methodology. One of the things that occurs to me first is maybe like a Markov chain or some model like that. What were some of the techniques you explored in the project?
The main model that has been used in the past to predict an individual's next job is exactly what you said. It's a Markov model. So it's a model that, to predict an individual's next job, only uses that individual's current job or maybe their previous two jobs, and also summary statistics about their history, such as number of years worked, and also other covariates, such as educational degree, other demographic variables. And so this, for a long time, and still is, a very common model that is used in econometrics. A lot of the time, it's a very good model, especially when data sets are small. There isn't a whole lot that you can learn from different kinds of career trajectories. So what will tell you the most about where the individual will work in the next year is the job they have now. If you want one job in an individual's history, it's just the current job that they have right now. So that's one standard model that we compare to. Another model we compare to, which we call a bag of jobs model, is similar to this, except it uses all jobs in an individual's history. So this is in some ways analogous to it's sort of, we can think of it as kind of in between a Markov model and the model that we use, which we call career. So the Markov model only uses an individual's previous job. The bag of jobs model, it learns what I will call a representation of every job. It combines every job in a worker's history to make predictions, but it doesn't combine them in a complicated way. It combines them linearly. Whereas the model that we develop not only uses an individual's entire job and their history, but also combines them in a non-linear way.
I think if I were to start on this day one, I would just take simple approaches, maybe make some dummy variables and stuff like that. But as you were describing it, it seems like you could have a different representation. Maybe it's an embedding or something like that, because two jobs could have different numbers but be quite similar. How do you capture some of those relationships?
Yeah, so that's exactly what we did. We built our method on learning representations of not only individual jobs, but representations of histories. And the high level idea is that there might be jobs that are very similar, although they're not exactly the same, but we should use the fact that they're similar in predicting an individual's next job and the kind of trajectories they take. So when I say representation, maybe the mental model that you should have in mind is a black box that takes as input every job that a worker has had in their career so far and just spits out a vector of numbers. And all that this vector of numbers represents is that it groups together workers with similar histories. If a worker has the same exact history as another worker, the representation will be exactly the same. But where the representation is the most useful is workers who have similar histories but not entirely overlapping. So, for example, if a worker has spent their entire career as a data scientist, maybe the representation should be similar to someone who has spent their entire career or has spent their career working as both data analyst and as a software engineer. So their histories are different, but in terms of what their next jobs will look like, these two histories probably look pretty similar. So the goal of representation is to group workers by the similar jobs they have in hope that it will help predict their next jobs. And that's exactly what we found. We found that the representation grouped together individuals with similar histories.
Well, deciding to use the transformer architecture, I guess in 2023, it's sort of a natural thing to do given how many successes transformers have had. But for some of the reasons you pointed out earlier, this job sequence isn't quite the same thing as natural language, even if we draw some analogies. What made you think transformers would be a good architecture that could tackle this problem?
So transformers were one of the first things that I tried for this problem. And that's because my background is in natural language processing, and it's in using transformer models as components of other models in NLP, language models, machine translation. So I was already very familiar with transformers, although I'd only used them for NLP. However, the transformers, although they were developed initially for NLP, they had been used before we started this project in a wide variety of other mediums as well. Maybe not a wide variety, but in some other mediums. So images, for example, is a popular use case of transformers, molecules in chemistry, and also even music, sequences of notes. What these kinds of data all have in common is that they all contain sequences of discrete objects. And that's sort of why the transformer felt like a natural thing to try here. The sequences of words differ from sequences of jobs in so many ways, but they both contain sequences of discrete objects. Here, a discrete object being a job, if you think of it as a discrete object, versus in NLP, a sentence or paragraph or book even being a sequence of discrete objects being words.
So the career model, as described in the paper, is a two-stage model. Can you break down what those two stages are?
The two stages that we use in the prediction for career are sort of our attempt to take the transformer model, which had been developed for text for NLP, and make it better suited to model sequences of jobs. And one way that sequences of jobs differ from sequences of words is that they tend to repeat. And that's what the two-stage prediction that we use in our model tries to incorporate. The model makes predictions in two stages. And the goal of the first stage is to make a very high level prediction about whether the individual will switch jobs at all. And if the model predicts that they don't switch jobs at all, then the next transition is pretty straightforward. It must be the individual's current job. If it then predicts that the individual will change jobs, the prediction sort of follows a more standard model that is used for natural language processing. In other words, it's a multinomial logistic regression where it can choose all the other possible jobs except for the individual's current job. And of those, try to predict which jobs are the likelier ones to transition to.
So my grandfather worked for 45 years at the same factory, and that's evolving. I've already beat him by quite a bit in terms of number of jobs. But you're going to have relatively short sequences compared to language. Does that pose a challenge?
Yeah, so that's another way that our data set differs from sequences of words is that depending on the data set used for words, there's sort of a maximum length to a career trajectory, which is probably around 100. I don't know if anyone has worked more than 100 years. Maybe you can check that later. But I think that's probably a safe upper bound. We'll say 200 to make it even safer. And then so when we looked at where the predicted advantage of career was coming from, we compared career to a traditional econometric model, this Markov model that only used an individual's current job and other summary statistics about history and other covariates to make predictions. And we found that when both models were tasked with predicting an individual's first job, their predictions were roughly the same. There was no comparative advantage in using career versus using the traditional econometric model. And this makes sense. The main advantage of career is that it uses an individual's entire history. So when there is no history to choose from, its predictions shouldn't be that much different or any different than the sort of econometric baseline. As there were more jobs in a history, we found that career made better predictions than the baseline. What's interesting is that in general, both career and the econometric baseline, they both made better predictions as an individual spent more years working. And one reason for this is that because as an individual spends more years working, they're likelier to stay in the same job. So if you think about when people tend to explore new jobs and transition, that tends to happen a lot more earlier in the career than it happens later. However, across these sort of career lengths, career predictions were always better than the baseline after an individual's first job. And maybe the best improvement came roughly between jobs 5 and 10, but that number depended across data sets. And so there's kind of a sweet spot where career has enough history to make better predictions than the baseline, and also early enough in a career that an individual hasn't tended to stay in the same job.
And what sort of metrics do you use to evaluate the model?
The main metric we used is a metric called perplexity. It's a metric that is used a lot in natural language processing. The main way to think about it is that it's a log likelihood. It's a transformation of a log likelihood. So our model it's a full probabilistic model. It doesn't predict just one job or two jobs. It considers all possible jobs in the universe, and that size of that universe depends on the taxonomy that's used to encode jobs. And it assigns to each of those jobs a number. So someone who has worked as a waiter, for example, may have, I don't know, a 70% chance of being a waiter the next year, but then maybe a 20% chance of being a job similar to a waiter, something like a bartender. Because each model makes a probability estimate for each job, one way to aggregate how well a model does is to look at the probabilities for all the true transitions based on what the model assigned. A model can't assign each possible job transition probability 1 because all the probabilities that the model assigns have to add up to 1. And so because this model has a constraint that it only has, one total probability that it has to divide across all possible next jobs, it's forced to give its best guess of the true probabilities that the individual will transition to. And so perplexity is just one way to aggregate all of the probabilities that are assigned by all the models of the true jobs that an individual takes next, and compare on average how high the model's assigned probabilities of the true job were. So if the model consistently assigns 80% probability to the individual's next job, it's going to do better than a model that consistently assigns 60% probability to that individual's new job.
And what's the role of transfer learning in the project?
So the role of transfer learning is that Although we care about survey data sets, these data sets are small. Because our approach is based on learning representations of history, the models that we use to learn representations of history, those that come from machine learning, are really best when they have lots of data to learn meaningful, high quality representations. So, for example, if we want to learn a representation of a data scientist being maybe similar to a software engineer, if those jobs only show up once or twice in a survey data set, most models won't be able to learn that those jobs are similar. What we had, though, was we had access to a data set containing passively collected worker profiles online that was provided to us by Zippia, which is a career planning company. And so this data set contained roughly 25 million worker profiles. And we can think of each worker profile as also containing sequences of jobs. So while these worker profiles may not be well suited to economic analyses directly, perhaps because they're missing important information such as demographics or wage, and also because they're noisily imputed and may not correspond to a true random sample of the population, it's difficult to use these data sets for economic analyses directly for these reasons. However, we were interested in taking advantage of the sheer size of these data sets, containing about 25 million resumes, that we thought we could be able to use it to learn meaningful representations and co-occurrences and career trajectories that we could then fine tune or adjust to make predictions on the small survey data sets that we actually cared about. So, put another way, although we still kept making predictions on survey data sets, and that's the thing we cared about, we were able to use the information that was encoded in the large data set of resumes to make the predictions on the survey data set better.
Fascinating. And can you expand a little bit on how those other data sets and the transfer learning process was able to improve the perplexity you achieved?
There are a few ways to break down the predictive improvement. So let's compare career, which uses a worker's full job history to make predictions, against a standard regression that only uses a worker's current or past two jobs along with the summary statistics. So we can think of there being three kinds of possible job transitions. One where an individual's next job is the same as their current job. Another where an individual's next job is not the same as their current job, but it's the same as the job they had earlier in their career. And finally, a transition where an individual's next job is a new job that they never had before in their career. So we see that career with transfer learning makes improvements over the regression baseline in all these categories. But the biggest source of improvement is when an individual's next job is the same as one they held earlier in their career, although not the one that they currently have. And this source of improvement kind of makes sense. By using all prior jobs, the model can assign higher probability to previous jobs that the individual is likely to transition to. We had some more analysis too to find out why the model was making better predictions for new jobs that were never held by an individual in their career. And we found the model was able to group together similar jobs and complete common trajectories. So, for example, one individual who's currently a student, but whose prior jobs included animal caretaker and engineering technician, this individual's next true job was biological technician, which we can think of as somehow combining information about being an animal caretaker, being an engineering technician, and being a student. And so career, which when it had used transfer learning, was able to assign a high likelihood of this transition to biological technician because it combined attributes from all of these related jobs in the individual's history.
And do you have any idea about how the prediction works as you look further out? Predicting my next job is a challenge, but a feasible one. Predicting my job in 20 years, I would love to know if you had any insights. I don't know what I'm going to be doing in 20 years.
Yeah, so one advantage of using a probabilistic model is that we can make those predictions. So most of the predictions I've talked about so far are an individual's next job, but because the model assigns a probability to each possible job, it can then, for the next year, it can then use the probabilities it assigns in the next year to make predictions for 2 years and 3 years and 4 years. And although the math gets kind of unwieldy, these sort of future trajectories can be estimated in a few ways, maybe with Monte Carlo sampling. So this is one other experiment that we did. We looked at how well the model does in the future. Although we focused mainly on 1 year out for now, the model we also looked at 3 years out, 5 years out, farther out to the future. We found something that may be intuitive, which is that the model's prediction of the next job, individual's next job, are pretty good, although the quality degrades pretty rapidly as we go further out into the career. So sorry, I don't have a good intuition for what your job will look like in 20 years, but maybe hosting Data Skeptic is a good guess.
I would love that. That would be great. We'll see if I can keep it up. Along similar lines, I think there's has to be some ceiling on how accurate this can be. I mean, at any moment, any individual could suddenly transition to being a realtor. There are certain things like that that on a data set might seem out of the blue, but people just want to change. So you can't be 100% accurate in these sorts of predictions. Are there any aspects you think that could drive the perplexity down or the accuracy up? Are there auxiliary features you'd like to have, or is it maybe it's more data from surveys? What could possibly better inform your model?
Yeah, so this is one interesting question. What is the best that a model could do? What is the Oracle model? There's always going to be some kind of uncertainty that we just never really know what individual's next job is going to be. And there's another kind of uncertainty that's a little bit more tractable, that we can build, better and better models that use all the information we have now to kind of get to the true best possible prediction given what we know now. So one experiment we did was we compared how we looked at how important the volume of resume data was to make predictions on the survey data set we cared about. And so recall that the resume data isn't being used directly to make predictions. We're not making predictions directly on the resume data. We're using it in some ways as a feature to try to make the predictions on survey data better. And we found that the quality of predictions scaled with a number of resumes that we had in our sample that we used for pre-training, for the transfer learning. As we had more and more resume samples, the model was able to make better predictions on the downstream survey data sets. So that's probably the first thing that will make prediction better, more resume data, just having a larger volume. So as we add more resume data, we should expect the model's predictions on the survey data to become better. So maybe that's a first order priority. So one other priority that will also improve the predictions of the model is more and more survey data, more and more of the smaller data set that we care about. If we can get that large, we're going to be able to make better predictions on that. So those are both, I would say, high order things that could improve the predictions of the model. If we've gotten to a point where including more survey data and including resume data doesn't make better predictions, then you're in one of two worlds. One in which you need to change the model or use other kinds of data or be more creative, and one in which you sort of have just maxed out and it isn't possible to make better predictions. Now, we're definitely not there yet, but I think if we get there at some point, that will be a really interesting conversation to be had.
Well, even if you're not quite at that point, it does seem this is sort of the best in class model available for making these sorts of predictions. With that in mind, how do you apply this? Who will now take the model and make use of these predictions?
So the goal of this sort of work we've done now is to put forward a general set of methods that can be used to analyze survey data. And although we focused on the specific task of predicting an individual's next job given pre-trained data of resumes, this approach of transfer learning is more general than that and doesn't need to restricted to predicting jobs. It can be, you can predict other things about sequences, such as an individual's wage, or B, it doesn't even need to be about labor economics. If you have other sources of large data and in other fields, there's no reason that the methods are limited to labor economics. Hopefully, the ideas here can be useful in other fields as well. So we hope that other social scientists, not only labor economists, but people in other fields as well, can incorporate the idea of transfer learning into their specific research problems. On my side, I'm working a bit on trying to extend these ideas. On the application side, I'm trying to use a model based on career to estimate adjusted gender wage gaps, and others on the method side, which is specifically career uses resume data to augment its predictions. But what happens when this data set is very different from the one that it's being used for analysis? In what ways can bias creep in? I think this question about bias and differences between resume data and the survey data we care about is an important problem for anyone who wants to use transfer learning to answer questions about small survey data sets. And I think that anyone who wants to use an approach based on transfer learning should first audit the model predictions and the data to make sure that it's clean and make sure that predictions aren't biased in systemic ways. So I'm also interested in developing methods for detecting and mitigating those biases directly.
So you have touched on a few directions you want to go with career. Is that going to be the main focus of your work going forward, or is this just one slice of your vision?
So career is the thing. Career and its extensions and offshoots is the main thing I've been thinking about now. I'm also thinking about similar questions methodologically to career, although maybe not relating to labor economics directly, things involving text and fairness and causal inference. Although before I do much more work professionally, I'm finishing up my PhD this spring, although my dissertation committee will have the final say on that. And after that, I'm excited to be starting a postdoc at Harvard this coming fall.
And can you share any details on some of the things you plan to work on then?
So as a postdoc, I hope to carry on this line of research, work on some of the applications I mentioned, work on some of the methods I mentioned, and more broadly, thinking about ideas in the intersection of machine learning and social science and economics, thinking about general methods in this area.
And is there anywhere listeners can learn more about the project or follow you online?
Yeah, I have a Twitter. The Twitter is my Twitter handle is Keyon V, Keyonv, and that has links to my website as well.
Awesome. We'll have both in the show notes for listeners to find it there too. Well, Keon, thank you so much for taking the time to come on and share your work.
Thank you. Thank you so much for having me. It's been great chatting.